In this paper, we investigate the supervisory control problem of timed discrete event system under partial observation. The supervisory control theory of discrete event system is a formal framework for the synthesis of control logic for complex automatic systems. And we're all familiar with, in this framework, the behavior of DES is restricted by a special supervisor that enables or disables events dynamically online based on its observation. Our work focused on an extension to DES where a special event tick representing the time unit was introduced. Corresponding to this extension, the framework of supervisory control also introduced the ladder control decision of force events upon a series of observable events. The system model and the supervisory control of timed DES were designed by Brady and Harmsworth in the 1994, and whereas Tajay and Ulysses work in the 2006. And our method of supervisor synthesis was mainly motivated by Ian and Laforge's work in 2016. In the TDS, the standard event was enabled or disabled normally, but for the TID event, it is enabled indirectly only when no feasible event was forced, and we can only disable it by forcing some events to happen. So see the figure on the top right. The event A was not forced, and the TID was enabled indirectly, but for the figure on the bottom right, the event A was forced by control decision gamma, and it is disabled indirectly. And from that, we can give a formal definition of the language generated by the TTS on the supervisor as like this. Now we can discuss the main problem solved in our work. Suppose we are given a TDS-G and a specification K, which is a prefixed closed sublanguage of LG. We need to find a partial observation supervisor S, which satisfies both safe and maximally permissive property. To solve this problem, several concepts were used. The first one is observable range. It denotes a set of possible states from previous states after seeing an observable event sigma. Note that for normal events, we just consider the next state after seeing transition sigma. But for TID, we also need to take into consideration whether a TID event should be preempted by some false event at some old state. See the I2 state in the figure. It was preempted by an event F from decision gamma F. Corresponding to the observable range, we also have unobservable range which predicts unobservable behaviors on the current control decision. TID events again should be discussed separately since it might have been preempted at some states. In this figure, the states in the ellipse were the unobservable range from the inner three states. And this is a formal definition of it. We proved two important lemmas about unobservable range. The first one indicates that our definition yields a reachability closure, and the second one means that for any state in the unobservable range of I under gamma, there is an unobservable path from F. The second one will be used in our most important theory. So let's say a specific example. We said that the I0 to be the set of 0 and 1 and 2, and gamma 0 to be the control decision where enabled event was all uncontrollable event and do not have force event. Then the observable range of O of I0 on the gamma 0 would be 3 and 4, which means if O happens, then current states should be 3 or 4. Now, if we make the new transformation gamma 1, where C was added to enable the event and O was added to the first event, then the unobservable range of I1 would be 3 and 4 and 5. We do not have 6 here because the teach event was preempted by O, since O is first and feasible. But if we pick transformation gamma 2, where O was not first here, then we should have the unobservable range of I1 under gamma 2 to be 3 and 4, 3 and 4 and 5 and 6 and 7 and 8, since T of here and here can both happen. From observable range and unobservable range, we can use the inclusive controller model, which uses the trauma-dim structure to analyze which states to be reached after observing some event and making some decisions. Note that the transition function we use in this structure was non-deterministic, since we did consider the consequence of different control decisions. The following is part of the gaming procedure. See the inclusive controller named T. Consider one of the initial states of this inclusive controller. And the first control decision is gamma 1. After gamma 1, the possible state of TDS is I1, which is the unobservable range of the single exterior. But if different control decisions were taken, then I1 could possibly contain totally different states of TDS. Now we observe an event OI. So the current possible states change to the observable range of I1. And then we may make control decision gamma 2. And the current possible states would become the unobservable range of it. Now we can give a formal definition of transition function in inclusive controller. Note that given inclusive controller T, we might consider several possible transitions, but maybe not all of them. If all the possible transitions were considered, we call this spatial inclusive controller a total controller with regard to G. This is a specific example of total inclusive controller with regard to the TDS of last example. So we can say that for the initial states, we consider all possible control decisions and their consequences, which means all the initial states, and then we explore the state space, and at each stage we consider all control decisions that could be made and all their consequences, and then we get a total inclusive controller here. Since we need a deterministic supervisor in the end, we also need a deterministic transition, and we denote it by uppercase H. We also extend it to clean star closure of the product of observable range and control decisions. Now, if we have some supervisor S, then it can generate a sequence of control decisions after observing a sequence of event alpha. So in the total controller, we can derive an estimation of possible states from this sequence, and we call it Q. We subtract alpha and S. Now we can prove the most important theorem of our work that indicates for any supervisor S, the estimation of possible event was indeed the events that could be reached after seeing alpha under a supervisor. Another important theorem claims that, given a supervisor S, it is safe if and only if the state estimation based on our total controller doesn't include any unsafe states. This theorem suggests an approach for synthesizing a safe controller. The approach to get a safe controller was simply doing a search from the initial states and explore the entire space, and then remove those who violate safety requirements, or those who become incomplete because of this deletion. And then we prove the theorem that claims all safe supervisors was included in the all-inclusive controller for safety. I used the term included before, and now I give the formal definition of it here. Again, we see the example given before. The AI safe for safety was in this figure, but without the dashed state and the transition. Finally, we introduced the procedure of extracting a supervisor from AI safe for safety, a new concept denoting how many events were enabled at the state of inclusive controller was given. We denoted by feed Q. It gives us hint which branch of decision to make is better. In the following part, I will again use a specific example used before to illustrate how to extract a supervisor from AI safe for safety. From the AI safe for safety obtained above, we will choose the initial decisions first, based on the number of feasible events after decision. So in this example, the green one we choose. Then we search through the AI safe for safety and do the same things above until all possible states was considered. Finally, we get an inclusive controller T star, which includes a unique supervisor S star. We claim and prove that the S star solves our problem 1. Before is the main content of our work. Our contributions are on the supervisor control of timed discrete-event system. We solved the synthesizing problem of safe supervisors for DES on the partial observation, and our solution is maximally permissive. We generalize some previous synthesis techniques from untimed setting to the timed setting. Our future work will focus on the problem of non-blocking for DDS. Thanks for watching.